Okay, let's talk about the rational function r of x equals x plus 1 times x minus 1 times x plus 3, all divided by x minus 2. There are many ways I can represent this function. This is factored form. Often when you see a rational function, it's not factored, it's expanded. So let's just see what this looks like if we expand it. First of all, x plus 1 times x minus 1. That's a special product. It's x squared minus 1. And you can use the distributive law and should be able to use the distributive law to verify that. Then x plus 1 times x minus 1 times x plus 3 equals x squared minus 1 multiplied by x plus 3. Now, by the distributive law, this equals x squared times x plus x squared times 3. In other words, x squared minus 1 times x plus 3 could be written x squared times x plus 3, and then minus 1 times x plus 3. So then minus x and minus 3. This is x cubed plus 3x minus 3, which equals x cubed plus 2x minus 3. Now, something's wrong. I said that wrong. X cubed times 3 is 3x squared. So this thing that I did here was just brain glitch. I have a lot of those lately. Okay, so we have this. All right, so r of x equals x cubed plus 3x squared minus x minus 3, all divided by x minus 2. Now, for very large x, the 3x squared minus x minus 3 is insignificant compared to x cubed. And that's for very large x, whether positive or negative. So I'll say for very large absolute value of x. For example, if x is 1,000,000, then x cubed is 1,000,000,000, which is 1,000,000 millions. 3x squared is 3,000,000. Okay, so that's like 3,000,000 versus 1,000 millions. Okay, like 3 parts in 1,000. That's a very small part. And the x and the 3 don't amount to a hill of beans. Now you can convince yourself of that. You can put larger and larger x's in here. You can put 1,000 in and see what percent this is of this. Okay, turns out it's 0.3%, I think. No, 0.03%, sorry. You figure it out. It's a very tiny fraction. So this thing is practically equal to x cubed over x. Now you can't ignore this x because it's dividing. Okay, of course, if x is a very large number, x minus 2 is practically the same number. What's the difference between 1,000,000 and 1,000,000 minus 2? Very tiny. Okay, so for very large x, the -2 in the denominator is insignificant. Now you can decide how insignificant is. No matter how insignificant you want to make insignificant, you can find an x big enough that the rest of the expression is that insignificant. Now you can decompress that entire statement. It anticipates the whole idea of limits at infinity and so forth. And it's well worth thinking about if you understand it. And if not, just understand this much. Also, I recommend if you do this, you don't just punch numbers into your calculator. You use powers of 10 and you cube them and square them and so forth, so you better understand how they work. People are in the habit of putting things into a calculator when they don't need to. You don't need to put a 1,000 into a calculator to cube it. And if you do need to, you need to learn. Okay? Okay. Now, you take this function, and we can start to draw its graph. Okay, for very large x, this function, which is the original function, but is equal to the function we have here. In other words, r of x is x plus 1 times x minus 1 times x plus 3 over x minus 2. If we expand that, it's x cubed plus 3x squared minus x minus 3 all over x minus 2. It follows from what I said here that the only significant terms are the x cubed in the denominator and the x in the numerator. So that this function is close to x cubed over x. Of course, x cubed over x is just x squared. So now, in looking at this function, we see that it behaves a whole lot like the x squared function. If we're far away from the origin, if x is very large, which means we're far off to the right or far off to the left. However, there's more to it. When x equals 2, the denominator is 0. If you have a denominator of 0 and a numerator that isn't 0, and you can verify that if x is close to 2, the numerator isn't close to 0. Matter of fact, if x is close to 2, the numerator is close to 2 plus 1, multiplied by 2 minus 1, multiplied by 2 plus 3. That would be 3 times 1 times 5, or 15. If x is close to 2, we have something, you effectively have 15 divided by a very tiny number. And that number can be as close to 0 as you wish. If you divide a number close to 15 by a number as close to 0 as you wish, you can get a number as big as you wish. Which means that this squaring graph doesn't do that. Okay? The squaring graph does something kind of weird. I mean, the R of X graph does something kind of weird compared to a squaring graph. Its values go off to positive or negative infinity. Its values blow up somewhere around x equals 2. Now remember, this is the x's that we have here are very large, and x equals 2 is indistinguishable from x equals 0 on this scale. Okay. If we want to go to the small x scale, could put x equals 2. Let's put it about here. This vertical line is the line where x equals 2. While we're at it, let's also figure out where this function is 0. You know, this is a 0 of the denominator. Denominator is 0 on the line x equals 2. Where is the numerator 0? Well, the numerator has factors x plus 1, x minus 1, and x plus 3. X plus 1 is 0 if x equals negative 1. So I can come over here to x equals negative 1 and draw a vertical line, vertical dotted line at x equals negative 1, just twice as close to the y-axis, but on the other side of the x equals 2 line. And then I can draw the x equals 1 line, which would be halfway between the y-axis and the x equals 2 line. And I'll label that x equals 1. And then the x plus 3 equals 0. That's at x equals negative 3. So I come over here all the way to x equals negative 3. I know the numerator is 0 at each one of these 3 points. Zero here and here and here. If the numerator is 0 and the denominator isn't, which is the case at these 3 points, then make sure I'm still on the screen, then we know that r of x is 0. So now I have 3 points where r of x equals 0. R of x is 0 here, r of x is 0 here, r of x is 0 here. Also, the only way it can be 0 is if I'm on one of these points, because any value of x other than negative 1, 1, or negative 3 won't give me 0. So the graph has to go through these 3 points. It has to blow up near x equals 2. And if I look at it zoomed way back, it looks like a parabola. So what does this tell me about the graph of the function? It tells me that the graph has to start up here. If I go far enough to the left, it's got to go way up. If I start far enough to the right, it's got to go way up. That means the graph has to come down way up there somewhere. Well, wait, one more thing I want to do before I draw this. I want to get the y-intercept. If x equals 0, that's going to be the y-intercept. Now, that's something everybody should be very familiar with by this point in a pre-calculus course. So I've got to assume that's automatic. Y-intercept occurs when x equals 0, because that's what the y-axis is. If x equals 0, we have 0 plus 1, which is 1, 0 minus 1, which is negative 1, and 0 plus 3, which is 3. So we would have a y-intercept on the line y equals 3. And the point, of course, is where the line y equals 3 intersects the y-axis. So now we come down from here. We go down. And now, okay, we come down and we hit this first 0 at x equals negative 3. Now we can't hit 0 again, and we're below the x-axis. How are we going to get up to the y-intercept at y equals 3? Well, fortunately, we have a 0 handy where we can just turn around and go up and hit y equals 3. Now, I'm not going to assume y equals 3 is the highest point in the vicinity of the curve here. We go up a little ways, we turn around at y=3, and we come down through the third zero at x=1. So come down through the zero at x=-3, turned around, going up through the zero at x=-1, went up and turned around a little bit before we got to the y=3, just because that's going to make the graph look about right. And went through the point 0, y=3, the y-intercept at 3, and then down through the x=1 point. And now we go down and approach the x=2 point as an asymptote. Then, and I'm not going to detail the asymptote, just giving you a general overview. Then we come down from the other side of the asymptote, and we've got to end up going up. We've got to be way up here in the asymptote, but we've got to end up going upward. So we're going to have to turn around. We can't go down through the x-axis. There's no more zeros. So we turn around and we go on up. That's what our graph looks like in general. Now in calculus, you learn to do some more specific things to the graph. Notice that the part of the graph, as we get near the x=2 line, acts a lot like the graph of 1/x. Yeah. And that makes a certain amount of sense because, well, it's like 1/x, or it's like 15/x minus 2. That's 1/x vertically stretched by a factor of 15 and moved 2 units to the right, which is going to be exactly there. So this is much like the power function, 1/x, but transformed, horizontally shifted, and vertically stretched. Okay, well, that's something to think about as far as rational functions go, and I recommend that you do.